This is Professor Jeff Wilkerson with an introduction to Project 2, measuring properties of the orbit of the moon from Astronomers as Observers and Experimenters, published by Kendall Hunt. So this is a project that asks you to get outside and measure the position of the moon relative to 2 or preferably 3 bright stars, and then try to deduce what you can about the orbit of the moon. And you can be as detailed or as simple as you want to with this. This is a project that I do most years with my students, one form or another. Again, not always exactly the same year to year, but this is a project that I do that is a group project, because the moon's up at all different times depending on where the phase is. And so it's a challenge to get the data. Sometimes you got to be getting that data at 2 in the morning and 3 in the morning. And so it's good for a group of 3 or 4 people to be sharing that work and to help each other out with the analysis, because it's a pretty good project, and it involves a fair amount of thinking geometrically and working on data analysis and thinking about how you want to use the data to determine the things you want to determine and exactly what you want to determine from this. And so this is a project that works well in that regard. And we want we want groups working on it here usually, and we'll have it stretch over as much as 5 or 6 weeks, sometimes a little bit more. You need a month to cover the full lunar cycle, and you know it's cloudy, and so if we could do 2 months, we get enough data to maybe make this actually work. Sometimes you don't. Sometimes it's just too cloudy and it's really hard, and you have to do a lot of extrapolating and discussion of what you see and how you would sort of interpret what you would see, despite the fact that there's not enough there to really say too definitively what's going on. But that's a real world project. So there's a lot of this stuff that is helpful in thinking about how real astronomy projects get done, and what the limitations of data sets are, what cloudy nights do to you, what sporadic intermittent data does to you, and sort of the challenges of being able to work with the night sky. This is even more challenging than the duration of the Sidereal Day project, because there you can find a few stars, and if you learn those stars and watch those stars move across the sky and figure out when they are where in the sky, you do pretty well. Since the moon is moving constantly against the background stars, you got to be able to find stars all across the sky to measure the moon relative to. And so this is a little bit challenging. Again, another reason group work is good. Help each other out to do this if at all possible. But the basic idea is to use a triangulation method to figure out where the moon is at any given time. So suppose you got a star here, and a star here, and a star here, and you go outside with your trusty angle measuring strip. You want to calibrate this thing well and do a good job with it, because you'll use it a lot if you're doing all of these different projects and all the different activities in the book. And so you measure how far the moon is from each of these stars. And then you draw a circle on a constellation chart. You draw a circle around that star that has an angular diameter, has a diameter that is that angular distance away from the star. One of the good ways to do it is, say, Arcturus right there. If Arcturus is one of your stars and you're 20 degrees from Arcturus, you move up 20 degrees in declination and down 20 degrees in declination, and mark, and then use a compass to draw a circle around Arcturus like that. So we would move here and here, and then use a compass to draw a circle around Arcturus like that. Beautiful. Bang. And then you do the same thing with another star. Oh, we missed that star, didn't we? You do the same thing with another star, and the same thing with another star, and the region where those things overlap, that's where you think the moon is. And the size of that overlap gives you some estimate of the uncertainty. It's not a perfect, all estimates of uncertainty are exactly what we call them, estimates. Not a perfectly measure of the uncertainty in the moon's position, because you might, just by luck, if you're only drawing 3 circles, you might get all 3 of them to cross at a point. And you know there's some uncertainty in your data, but this is at least an estimate of what's going on right there. And so you would say that's where the moon is, and you would read it off. You get the right ascension and declination that you would read off. You drew a circle around Arcturus, and you drew a circle around Spica, and you drew a circle around Antares, and you'd have the moon in here someplace, for example, like that. And you read the center of that area is the right ascension declination. You could do this with just 2 stars. And so you could do this with just these two stars, if you do really good sketches, and you should draw really good sketches as you go out and do this, take as much information down as you can. And if you just had these two stars, I'll redraw that over here. If you just had these two stars, then you have a crossing point there and a crossing point there. And your sketch should tell you, oh, it was to the left of these two stars. So let's get this point, right? And so you could tell this is the point it was, not this point. It's harder to get an estimate of the uncertainty right there. But then you got to turn that into some sort of model of the orbit of the moon, whatever it is you want to understand about the orbit of the moon. At a bare minimum, it would be good to look at this and to say, you've got your ecliptic path across here. And you can look at this and you can say, that position that we just found is right here. I can measure, that's where the sun is. That's the plane of the solar system right here. I can measure the position of the moon at that right ascension. The moon is how many degrees above or below the ecliptic. And that's a great piece of data to start with, is to get the difference of position of the moon from the ecliptic as a function of time, as a function of phase, okay, as a function of how full the moon is and whether it's waxing or waning. And so you've got this information about the phase, and you've got the moon's declination at the given right ascension minus the ecliptic declination, whoa, at that right ascension. And so then you can say, was the moon above the ecliptic or below the ecliptic? By how much? How uncertain were we about that? Here's the theory that's behind this. The philosophy that you're using is to say, if the orbit of the moon is perfectly aligned with the orbit of the Earth around the sun, then the moon is always going to be right on the ecliptic. That's by definition of what's going on, and that number is always going to be 0. If the orbit of the moon's tilted a little bit, that's going to go from above the ecliptic to below the ecliptic. And its maximum amount above or below the ecliptic is related to that tilt angle, right? And so it's going to be increasing, 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 decreasing, 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 decreasing. And so you're not going to have data for every night. You're going to have to do extrapolation. You're going to have to look between points and say, if I make a graph of this as a function of time or as a function of phase, then it might look like calling phase 0 to 100%, where this is, instead of phase, it's really cycle. It's really portion of the cycle that the moon is. So new moon, back to new moon. New quarter, full, third quarter, back to new quarter, third quarter, full, third quarter, good grief, I'm not doing this right at all. So this would be new. That would be first quarter, that would be full, that would be third quarter, that would be back to new, and you've done a complete cycle across there. And you might see this thing, you might have a point that's there and there and there, and you might have to interpret something that looks like that and to say there's how far it can get above or below the ecliptic. And where is it in phase? That's going to tell you the orientation of the orbit, of the moon's orbit around the Earth relative to where the Sun-Earth line like this. If its maximum amount, if it reaches its maximum amount above the ecliptic when it's full, then you would say, oh, look at that. Here's the sun, here's the Earth. From the side view like this, the moon's going to be full when it's out here, and so it's going to reach its maximum amount up there, or something like that. If it's new, then it's going. If its maximum amount is above when it's new, it's over here. Most likely, it's somewhere in between there. You got to draw other figures and other orientations to get a sense of what that plane looks like oriented relative to the Earth-Sun line like that. A lot of good information in there. If you have detailed enough data, you can do other things. You can start to say, does the moon appear to move from one night to the next? Does the motion of the moon appear to be constant in speed? If it's an elliptical orbit around the Earth, you would certainly not expect it to be constant in speed. You would expect it to be faster when it's closer to the Earth and slower when it's further away. My guess is you don't have detailed enough data to be able to do that, but it's a good question to ask, to say how good would your data need to be able to see that? How good is your data? How well do you know the positions of the moon that way, and how much data do you have? And so you can start to try to build these kinds of geometrical models, again, from triangulation on the sky, and start to see how the moon is moving across the sky, what the orientation of the moon's orbit is, relative to the Earth-Sun orbit and how it's inclined. So that's what we're trying to do. That's the main thing. There are other things you could probably do. You could probably try to estimate the phase of the moon, how full it is, how long it takes to go from one phase to the next phase if you want to do those sorts of things. But this is your basic introduction to what this project is largely about. And as with other projects that we do, the sort of goals, if you will, of this project are as much learning about the moon. So you have the goals for learning about the orbit of the moon, but those aren't the only goals that I would associate with the project. If I'm asking students to do this, I'm going to look at this and say, trying to do this kind of geometrical thinking, taking data and turning it, doing the kind of geometry that you need to do to turn it into a real model of the geometry of the solar system is an art. And if you go way back to what we talked about at the beginning, where people confuse art and science, it is the art part of, it's what people call the art part of what is the scientific process, to say that's where you're thinking, where you're envisioning, where you're imagining what's going on here. And so that's a really valuable experience, and that's what this exercise for me is as much about as anything else, as well as figuring out how to overcome obstacles in measuring and data analysis. To say these are hard measurements to make. It's hard to know what stars are what on the sky. You got to work hard on it. You're going to make mistakes from time to time. You got to know what to do with the data when you make these mistakes from time to time, and so on and so forth. So this is good. I hope this makes sense to you. I hope you can make some meaning out of it. And this is a project that I really encourage you all to try to do during the course of your use of this textbook, because this is really a powerful experience. Just another learning outcome right there is just to get a feel for the motion of the moon against the background stars, and to recognize how much the moon moves from day to day and how that's related to phase. And so this is another really important good thing, and I think it's worth spending the time to make these measurements and do that, even though some of them have to come at awkward hours in the middle of the night. So good luck with it, everyone. Hope you have fun with it. I certainly enjoy this one, and see what you can learn about the orbit of the moon and about doing a project like this.